Welcome to the Omar Alayli podcast, your go to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Alayli, and today I'm thrilled to have a special guest joining us, Michael Staab. Michael has an impressive career as a systems engineer, working on both robotic and human rated spacecraft missions, specializing in fault management, system autonomy, avionics, and mission design. He's worked at NASA's Jet Propulsion Lab, Northrop Grumman, Blue Origin, and now at ICON. Michael, it's a pleasure to have you here.
Yeah, thanks, Amar. It's good to have me on. Looking forward to the discussion.
First things first, congratulations for the NASA JPL on the successful launch of the Europa Clipper spacecraft today. They were doing the engineering development of the spacecraft during your time at JPL, if I'm not mistaken, right?
Yeah, that's been a mission a long time coming. I think the project scientist has been working on that mission something on nigh 25 years to get it off the ground. So yeah, JPL missions take a long time to develop, but once they get going, it's always very exciting. Really, really looking forward to what they discover when they get to Jupiter, which is not for another 5.5 years.
Michael, your career kicked off in an amazing way, as I said, at NASA's Jet Propulsion Lab as a flight controller for the Cassini spacecraft, right? You were part of the Cassini's final mission phase to Saturn. And can you tell us what it was like being behind the controls during such a critical time? And how did it feel to be part of such a legendary mission?
Yeah, I started JPL right out of Georgia Tech, getting to fly Cassini, which was always one of my bucket list careers to do, was to get to actually fly spacecraft and be the one that actually gets to operate it. Um, like you said, I did get to come. I came in at the tail end of the mission. During the last parts of the actually was there for the last Enceladus flyby. So hopefully, kind of like Europa, we'll get something in Enceladus here in the next couple of decades, to see what also is under its icy shell, because it's also an icy moon. It's got a subsurface ocean, and actually has water geysers that we've detected down there. So that's another interesting moon. But yeah, I was one of the last aces that was trained up. So I got to fly Cassini for about 2 years. Was there for, at least I think, the most exciting part of the mission, which was the proximal rim plane crossings, where we actually shot the roughly 1,700-mile gap between the top of Saturn's atmosphere and the edge of the rings. Um, from a from 1.5 billion kilometers away, being able to navigate through that very very tight window. So that was a really great experience, a lot of fun. Actually, several of the Europa Clipper flight controllers in the critical events room today were Cassini engineers that I got to work with. So it's great to see folks still there and still exploring the solar system. It's intoxicating. It's hard to leave it.
Michael, I have to ask, were you always this focused and determined on working in space? Like looking back, were there specific moments or experiences that pushed you towards this path?
I think, like most in this industry, we can usually point to like one or two events that kind of really got us on this track. And the two that I particularly remember was the landing of Pathfinder, which was July 4th of 96. I think it was July 4th of 96 or 97. I'm going to get my dates wrong. Um, but I was not even 10 years old at the time. And we were watching the landing at my grandparents' house. Because it was a big deal. It was on the 4th of July. Um, and NASA intentionally always always tries to have big spacecraft events on critical holidays, because it's we can make sure that everyone celebrates it. But I got to watch, we watched Pathfinder land on the surface, and the first images back, and I remember turning to my parents and it's like, I want to do that. I want to go to Mars. I want to build spacecraft to go to Mars. And then the second piece, which came only like a year and a half later, was John Glenn's space shuttle flight. We watched that from the library at school, and I was, I think, just 10. I just turned 10. And I came home that night and told my parents I'm going to be an astronaut. Not that I think that I'm going to be selected as an NASA astronaut, but the fact was those two things were sort of like the driving mechanisms that for a lot of us in the space industry that really push us to want to work hard at school. And we have a clear cut goal. We're going to go work for NASA. We're going to go uh, for a lot of kids coming out of school today, it's I want to go work for SpaceX, or I want to go work for Blue Origin, or a lot of these space startups, because that's the fancy, cool, new everything. They're doing all the really cool stuff that everybody wants to be involved in. So, um, just like yesterday with the Starship flight test number 5, and they caught the booster on the chopsticks. Like that, if that doesn't inspire a whole generation of kids to want to become engineers, I don't know what does, because that kind of stuff is the same sort of moments of landing a rover on Mars. or
If I didn't see it live on TV, I would have thought this was CGI or something just amazing, out of this world.
Yeah, I mean, credit to SpaceX. They're turning science fiction into science reality. That um, for for the engineers, we look at we look at that and say, it's just a very complex systems integration problem, and it's a challenging controls problem, but it's a controls problem that can be solved. It's basically an inverted pendulum. But no one 10 years ago said you would land a rocket vertically. No one said that you would do that. I think some of the old studies for NASA were we were going to put wings on boosters and we're going to fly them back like a space shuttle. And of course, you never saw that.
Yeah, and don't put legs on them too. So
Yeah,
it's
no put
like,
legs on them. It really takes. At JPL, we sometimes call those ideas. They're just crazy enough to work. And landing a booster on some chopsticks, it's just crazy enough to work. The physics doesn't break. It does work. And kudos to SpaceX. They keep proving the industry wrong. I mean, I'm no longer a denier. SpaceX says they're going to do something. I believe they will do it. It may take them a couple years longer than they quote, but they're going to do it, because that's just the SpaceX mantra. They set out to do a goal, and they're going to do it.
let's get back to space systems engineering, right? Can you break it down to our listeners who might not be familiar with the field? What does a space engineer do? What does it take to become a space engineer, a systems engineer?
Yeah, we kind of have to break down what is a systems engineer. Systems engineers, from my perspective, having done this job for almost 8 years now, a systems engineer is not really a traditional discipline within engineering. I'm not a systems engineer by training. I'm a rocket scientist. I have degrees in aerospace engineering, so I study fluid mechanics and structural mechanics, uh, control systems, fluids, propulsion, all sort of those things that are fundamental to building airplanes and spacecraft and rockets. Um, the systems engineering piece comes in when you actually have to build something as complex as a Falcon Heavy, or as complex as a Starship, or as complex as a Europa Clipper. And we tend to like to say that a system, the old definition of a system is a sum of all of its little parts. The complexity of a system really begins to show when you have lots of parts and lots of interfaces. The more interfaces you have, the more components, the more parts you have. That's when a system becomes complex. That's sort of the old way of talking about what a system is. The new sort of definition is it is about the sum of its parts and the number of interfaces, but it's also about the interactions with the environment. And that's a newer term where we talk about emergence. System behaviors emerge when a system actually begins to operate in its environment. We can design a spacecraft to be design it to a level where we can sort of understand all the top level behaviors and what the system's going to do if certain things happen. But the one thing we can't control is the environment it operates in. Going to Jupiter, high radiation environment, you're going to get smacked with the radiation all the time. And it's only when you actually put the spacecraft in that environment, you actually see that emergence. Um, the traditional way of system engineering that a lot of people think about, it's about requirements, it's about interfaces, it's about verification and validation and things like that. But there's a lot more to not just the field of systems engineering. There's a lot more to how you actually be effective as a systems engineer. A lot of it is knowing how to be a good interdisciplinarian, good cross-functional engineer. I have to basically know everything, or as much as I can, and I always use the term just enough to be dangerous. I need to know just enough about all the subsystems, all the components, and how they all integrate together, so that I can understand if I make a changeover in a fluid subsystem, I know what the impact's going to be to the propulsion system, what's going to be to the thermal system, how it's going to change avionics, how it's going to change structures, how it's going to change power, how it's going to change software. It's really having this mindset that I was taught at JPL is called systems thinking, and that's being able to understand how changes, little minute changes over in this one little product, have an impact on everything else, and you have to assess um, all the different impacts that that change will create. So it really is sort of a synthesis of pretty much every subsystem for a space vehicle that you can think of. You've got structures, you've got mechanisms, you've got power, avionics, fluids, propulsion, telecommunications, software, as well as the interfaces towards the larger pieces of the system. If we start talking about system architecting, where we have a space vehicle, but that space vehicle also attaches to a launch vehicle. So now we have to make sure that the interfaces with the launch vehicle are correct. The electrical connections are correct. The software connections are correct. The avionics connections are correct. Uh, the actual launch vehicle adapter that pushes us away from the launch vehicle. It's really understanding the full system context, which really thinks about not just the system that you're making, but how it interacts with everything else around it, all the external systems, whether they be ground stations, other satellite communication networks in space, how they interact with operators, not just the people that operate the vehicle, but folks that might be integrating the spacecraft, folks that might be doing launch preparations. Um, it really forces you to have that very high level, sort of, we talk about that 100,000 foot view of the whole system, but also got to have the knowledge to dig deep into the system design and really get down to the individual signals, the electrical circuits within avionics, to understand if I send this particular command that's encoded in binary, it's going to then create an electrical signal at this this serial communication interface that's going to be measured over a wire that goes to a component, which then reads that information and does something with it. It's really digging down, sometimes as deep down into the system as possible. So, how you become a good system engineer is you first have to have good foundational engineering knowledge, like aerospace engineering, like mechanical, like electrical. But then you got to start getting into, you got to learn a lot about every system. And that just comes with experience. It really does. It's not something that someone right out of school is gonna walk in and is gonna pick up, every little thing about how software and avionics and power all integrates together, as a system, and how even to write good requirements. This is always a thing with junior engineers that I talk with, but also with students when they ask, "Oh, I want to be a systems engineer. How do I become a good systems engineer?" And I will always ask them questions of, what is a good requirement and how do you make it? It's usually a blank stare. And it's because you just don't have the experience. You just don't know how to do that. I've been doing this for a while, so I understand how to translate objectives into ConOps, how to write requirements, how to write good requirements that I can actually verify, how to translate that into analysis to actually prove that my requirement has some leg to stand on, rather than it just kind of exists. I don't know why. It's just there. That's the very SpaceX Blue Origin new space sort of approaches. We try to almost aggressively get rid of requirements as much as possible, because if I have a requirement, I got to verify it. And verification, depending on how you're verifying it, can be really expensive and time consuming. It takes up a lot of resources. So you want to make sure that if you actually need that requirement, have it written down. And if not, get rid of it. We can test it internally. We can do our own sort of stuff where we'll verify stuff internally, but we don't actually have to have that requirement that we have to have formal verification evidence to prove that we actually did it.
It sounds to me like becoming systems engineer is a bit like becoming an astronaut, old school, not tourist astronauts, you know? What I mean by that is you start by becoming incredibly good at one thing. Like a lot of astronauts began as fighter pilots, but over time, you develop a big picture view that lets you manage or design the entire systems. What do you think?
Yeah, the difference between what I call a big A astronaut and a little A astronaut. Little A astronaut would be, there's this debate all the time in our industry about someone that flies on a SpaceX rocket that pays for a capsule, or someone that flies on a Blue Origin capsule or a Virgin Galactic. Um, uh, I'm forgetting what the name of the vehicle is now. Are those astronauts or are they passengers? My view is more of you're not paid to go up there. You're not paid to be on that flight. You paid someone else to do it. Big A astronaut would be someone that's paid to go into space. NASA astronauts, ESA astronauts, they're paid to go into space. They're paid by their governments. They're highly trained to fly lots of different spacecraft, and they're specialized in how to operate space systems. If I were to go fly in a Blue Origin capsule today with New Shepard, I'm a little astronaut. I'm just there for the experience. I don't know how to operate that system, and New Shepard was designed that way. It's not designed to have a dedicated operator that knows how to fly the vehicle. It's all run by software. You just sit down, buckle yourself in, and off you go. Dragon is another example of Dragon was designed with the intent of you don't need a dedicated big A astronaut to fly Dragon. I mean, it does have that interface because NASA likes those interfaces. They like their astronauts to be able to interact with the system. But Dragon, for the most part, can be operated entirely by software and the ground. You don't need a pilot in there. But yeah,
So, you mentioned it earlier. Have you applied to becoming an astronaut before?
I have gone through 3 application rounds now. Um, the current call, I believe they're starting to invite people down to Johnson. I haven't heard anything, obviously, or else I'd be a little bit more excited. But that's just kind of the nature of the application. There are thousands of people just like me that are highly educated, highly experienced, lots of diverse backgrounds. It's hard. It's hard to stand out. Um, it's hard to get a call when there's 5,000 other people that are just like you, and they only have a slot for they only have slots for 10 to 15 people at most. It's very competitive. So that's just how it goes.
Yeah, but even if you haven't been able to get a chance to go to space, you already have a design that you worked on that have gone to space, even to Mars. You've worked on designing some fascinating missions like the Mars Exploration Perseverance rover. When you're designing a mission, what are the big things you need to consider right from the start?
When we talk about the synthesizing a program, the first thing that as a system engineer I always care about is the objectives. What are we doing this mission for? Um, because the objectives really help drive everything else that the system designs. The way that you architect a system, the concept of operations, how you plan to operate the system, how the system integrates with the environment and all the other external systems with it. That system context we were talking about. The objectives really are the top level. And for a lot of the NASA missions, those are usually driven by some kind of national space policy. Either we're going to return people back to the moon, we're going to go to Mars and collect samples that we might return someday. It's unfortunately where Mars sample return is for the United States. It's in limbo. We have some samples that are on Perseverance. If and when we go get them is likely sounding like it's going to be a commercial provider that's going to go grab them. But it always has to start with those objectives. So if we're talking about a Mars mission is a great example of an objective. We have science teams that come and tell us, you mentioned MER, Mars Exploration Rovers. Um, we have scientists that come to us and say, we want to go look for signs of water on Mars. Great. The geologists will tell us they know specifically the things that they need to look for in order to detect water on the surface. So, as mission designers, when we're kind of starting with those objectives, we first kind of have to look at the orbital mechanics, and this is where sort of the fun part of mission design and high level con ops and system architecting gets into. It's we first have to look at the orbital mechanics of, well, how do you get there? So that's kind of where I started with the foundational knowledge of engineering. Aerospace engineers, we learn orbital mechanics. So the foundations of orbital mechanics is, well, how do you get from the Earth to Mars? And that's usually an optimization problem where we try to minimize the delta V, because delta V is everything in a space mission. The amount of velocity change that you need to perform your mission is the most impactful technical performance metric for the whole system. It drives everything. Um, it drives the sizing of your propulsion system. It drives the sizing of your thrusters. It drives how much propellant you need. It drives wet mass, which drives the launch vehicle that you need, how much structure you have to hold, or how much structure you have to build to hold all this weight. Um, just because we don't technically have gravity in space, we do have to survive the inertial loads of launch. And we also, have to move that mass. Inertia doesn't just go away. We still have to be able to move it. So the delta V really, really drives a lot of the decisions with a high level system design. So if we want to send something to Mars, let's say we want to send a rover, we can predict fairly easily when we should launch and how much energy it's going to take. If you've ever gone to the NASA websites and looked up the Earth Mars pork chop plots, that's what we call a pork chop plot. It basically gives us the representation of departure date versus arrival date, and gives us basically contours of constant, what we call C3, specific excess energy. And that's essentially the square of how much velocity that you need beyond escape to get to Mars. So typical Mars C3s, somewhere on the order of 3 to 4 kilometers per second. So to escape Earth gravity, you already have to be going really fast. And now we have to add another 3 to 4 kilometers per second on top of that in order to get ourselves into essentially a Hammond transfer, which is the minimum energy solution to go from one place to another in space, between two objects. So we kind of know what that all is to start with. And having all of that sort of delta V sort of budget of how much we need. Now, there's other stuff we put on top of that. It's not just, that's typically just what the launch vehicle has to give us. Launch vehicle's got to give us this much. But we also carry propellant with us because we have to do trajectory correction maneuvers. We have to do maneuvering in space because
change planes.
Depending on what your architecture is, your solar producing system, which is typically a solar panel, is not in the same plane as your telecom system. They may be in different places. So if you want to turn towards Earth to talk, you're now off axis to the sun. So you're not producing as much power. So you need propellant or another type of attitude determination solution like reaction wheels or other stuff like that to be able to maneuver your spacecraft while you're cruising out to Mars. So we have to budget for the TCMs, how much we're going to use, and then put margin on top of it. Systems engineers love margin. We put margin on everything. We put it on our power budgets. We put it on our mass budgets. We put it on delta V. We put it on telecom, pointing, everything. Any single system budget we have, we put margin on top of it because we know in the early parts of design that the maturity of the design is very low. We're making a lot of very broad assumptions about how the system works and how the system is designed. So we carry a lot of margin up front. So as the system matures, we know that we're going to start losing that margin. We know that we're going to start gaining mass. That's just an inevitability. It's based on both some heuristics from NASA and in the United States, the DoD, because we've built lots of spacecraft, lots of very complex aerospace systems before. We kind of know, based on past history, how things are going to grow. So that's why we have that heuristic number on top. But we also know that as the design matures, we're going to find things that are unexpected. We're going to discover that, hey, that particular, we realized that our propulsion system, um, one of the valves that we were assuming we were going to use, is incorrect. It's not going to give us the performance we need, and we got to go design a new one. And unfortunately, it's going to weigh twice of what we originally budgeted. So a systems engineer would say, yeah, that kind of is unfortunate, but we have the margin to support it. And that's when you start getting into baselines where we're very, very stringent about watching our system budgets very, very carefully, our mass, our delta V, our power, so that as we get closer to integration and we start going to test, we've got some margin still on top of it, knowing that even in final systems integration, hey, we had to put a shim between two parts because the tolerances were just a little out of spec and we didn't have time to go make a new one. So we're going to put a shim in there. We still got some mass margin to give. And the reason we watch those margins so carefully is because one, it drives the delta V budget. So we design our spacecraft very specifically to have this much delta V. And if you know anything about the traditional rocket equation, it has that nasty little logarithmic of the mass fractions, right? So if you want to have so much delta V, you've got to burn so much mass. That's just the nature of the universe. If you want to go anywhere, you have to expel mass. No one has yet created a system where we can get energy without having to consume something else. That's just how the universe works. So we have to watch those budgets very carefully. And if we're over mass, we don't have enough propellant now because our tanks aren't big enough. We don't have enough propellant now to complete our mission. So that means that now we've got to figure out something with the trajectory, or we may have a bigger problem. But the other side of that is a lot of these launch vehicles have very specific mass tolerances that they can accept. You can't go over a certain budget or a certain mass when you're integrated with them, and you also can't have your center of gravity so far above the integration plane, because otherwise you get those high bending moments uh, during launch that could cause your spacecraft to separate from the payload adapter. That's also not good. Um, so very high level. To answer your question, we start with objectives and we go through orbital mechanics and ConOps design and systems analysis to really make sure that we've got a really good understanding of how much mass is it going to take, um, how much delta V do we need, when are we going to launch. Schedules are very important. If you want to go somewhere in the solar system, you usually only have like 2 week window to go. So like Europa Clipper, Hurricane Milton just came through. And you've only got 2 weeks to launch, because if you don't launch within that 2 week window, then Mars, where you're trying to get a gravitational assist from, isn't going to be there when you arrive. It's going to be gone already. So now you don't have enough delta V, and the missions. That's sort of the advantage of flying a gravity assist trajectory, but also the risk. If you miss your window, you can't go, because all the planets have to line up in the exact right place so that you can pick up this gravity assist, and also so you can hit Jupiter 5.5 years from now, where the trajectory is actually aiming where Jupiter is going to be 5.5 years from today,
from now. Yeah.
not where it is
But
right now.
by the way, is it directly heading to Mars now, or is it gonna do a gravity assist with the moon first?
So it's actually going to do two gravity assists. And this was part of the trade off when Europa Clipper was bumped off of the Space Launch System, because Space Launch System is having their own scheduling issues, so they weren't available. If they had an SLS, they could do a direct transfer, which is crazy to be able to do a direct transfer to Jupiter. But Falcon Heavy doesn't have that capability to go direct transfer. Starship probably does. Starship probably definitely does, but SLS wasn't available. All they had was Falcon Heavy, so they had to go back and redo their navigation, their trajectory, and their navigation solution out to Jupiter. So now they're going to pick up a Mars gravity assist. I think sometime. I want to say I heard it was sometime early next year, um, and then they're going to fall back down into the gravity well, and they're going to pick up an Earth gravity assist as well. And that Earth gravity assist is going to give them enough delta V to basically throw them out to Jupiter. And
Okay.
that's why the cruise went from about 2.5 years to 5.5 years, because they have to spend
Okay.
time out there picking up gravitational assists from Mars and Earth in order to get themselves out to Jupiter.
From your perspective or a systems engineering perspective, how does the requirements for crewed and robotic missions differ?
Well, the most obvious requirements are you don't have to keep your rover at a nice balmy 75, 80 degrees with at least 5 pounds per square inch of oxygen to keep them conscious. You don't need a pressure suit. You don't need an environmental control system. You do need some radiation. Uh, you do need some sort of radiation shielding of some kind, usually of just your more sensitive electronics. Um, but for the most part, you don't need radiation shielding. You don't need to be carrying these large tanks of water or these lead lined holes holes HULLS, not HOLES. I know in the English language it sometimes sounds the same. We don't have to carry all these very sophisticated radiation systems to keep, as we kind of say in the space world, to keep the squishy occupants inside still alive. The other big issue that you and I have talked about in the past is the logistics of water and, well, just consumables, oxygen and water and food. Like those things spacecraft don't need. As long as a spacecraft has solar energy, which usually comes from the sun and solar panels, and as long as it doesn't get too hot or too cold, it's happy. It can, those spacecraft on Mars for MER, if it wasn't for a dust storm, I'm confident that Opportunity probably would still be going today, another 6 years later, because at the last good day we had of energy off of her, we were still generating 900 watt hours of energy. We still were thermally very, very happy. As long as the environmental conditions don't change, a spacecraft essentially can keep going forever. What really ends a spacecraft life, especially an orbital spacecraft, we'll go back to Europa Clipper. What eventually will end Europa Clipper's mission is it runs out of propellant. It runs out of the ability to maneuver. It was the same problem with Cassini. Cassini was running to the end of the amount of maneuvering propellant that it had left. And just like Europa, um, there may be life there. We don't know. Europa Clipper is it's not a life detection mission. It's a life surveying mission. It's looking for, does Europa have the necessary ingredients to support life? Does it have water? What is the pH of the water? Are the right chemical constituents down there? Is there an energy source to feed the organic chemical reactions that create more complex life that we find at hydrothermal vents on the seafloor of Earth? That's what Europa Clipper is looking for. But because it's such a precious, um, uh, because it's such a precious, um, I'm going to just use the word target. Because it's such a precious target of observation for scientists, because we think there might be life there, we don't want Europa Clipper to smack into it. Because
Okay,
no
that
matter
was my
how good we
question.
are at keeping
Okay.
our spacecraft clean, we can't guarantee that it won't have some bacteria that traveled with it from Earth to the Jupiter system. And it always comes back to this age old question: if you find life, and we find it with a spacecraft that we built and sent to Mars or Europa or Enceladus, was that life there to begin with, or did we take it with us? That's the age old question of planetary, not just planetary protection, but of anyone that's trying to answer the most foundational question that humanity has ever asked: is there life elsewhere in the universe? So the hard part is making sure we didn't take it with us. So Europa Clipper, just like Cassini, will eventually run out of propellant, and that will eventually end its life. That is the one resource that isn't basically regenerative. We can't replace our propellant to keep maneuvering. We've got plenty of solar power. Got plenty of solar power out of Jupiter. We just don't have enough propellant. So eventually, when Clipper gets low on gas, likely what they're going to do is they're going to send it in Jupiter. just like with Cassini. They're gonna send it into the atmosphere of Jupiter and burn it up, so it can't possibly hit uh, Europa down the road.
That would be an awesome
Yeah,
scene. Well, yeah, we just talked about it earlier about the SpaceX launch yesterday. It was amazing how they were able to catch the booster on the what do they call it, the Mechazella tower on the chopsticks.
yeah, I've heard
That was
it's.
just
I've heard something like Mechazilla, the chopsticks.
Mechazella tower. Yeah, 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 the chopsticks. You got a chance to see it, right?
Yeah, I watched it live. Very impressed. Very impressed by the engineering, and really the thing between even integrated flight test 4 and 5, you can see um, that SpaceX is learning, and that's always been the difference between SpaceX and a lot of other space companies is they are not afraid to take the approach of fail fast, learn fast.
As you said, see, like SpaceX seems to be approaching mission design differently, like testing systems in phases, making updates as they go, instead of designing an entire mission of his spacecraft or even the spacecraft and simulate in the computer software simulate it and then design it, and then we'll see. Hopefully, it'll work out, or we have to do the kinks and then we're out of budget. Does that sound like what's your take on this approach? Do you think this iterative hands-on testing is the future of mission design, or what do you think?
Well, I think that's always been the most efficient approach to doing concept development and systems engineering is it has to be iterative. Um, we get to a point in our analysis and our design where we basically hit up to a wall where we've gotten to a point in our design where we can't learn anything else unless we go actually try something. If we go build something and go operate it and go get some data and learn from it, because our designs are always based on assumptions. We make some assumptions about how the system's going to work. We design via requirements up to that point, and then what do you do? The traditional way at NASA is we do lots of analysis. We go through hundreds of design cycles to get to a point where the whole system is basically well understood down to even the integrated circuit level. We know how all the circuits are laid out. We know all of the interfaces down to, very, very, very specific detail. And then we can go build
Before physically building it, even.
before building it. And that's the very traditional way of how governments fund programs, because governments traditionally don't want to release funds until designs are complete. Because once you cut parts, the age old saying is that once you cut parts, that's when the cost starts to show up. If you're just playing around with paper and you're playing around with bits and computer programs, you're not really taking on any risk to cost. And that's the very traditional way of how governments sort of fund space programs. ESA, it's just like NASA, it's the same way. We got to study for 20, 30 years before we make a decision on what we're going to do. The SpaceX approaches and the Blue Origin approach, more of this tradition, more of these, new space startup sort of environments is we have a rough objective, a rough idea of what we want to go do. We're going to use our past experience to help inform what we're going to do. We're going to go do some designs, make some assumptions, and then we're going to go build something and test it. Because at some point, our con-ops are only as good as the assumptions we put into it. So let's go make a star hopper. Let's figure out how we would integrate Raptors on a Starship, a tiny little tank with some legs. Let's fly it off. Let's hover for a little bit and let's go back down. We're just testing the con-ops. We're testing assumptions based on other things that we've done. And then the next iteration is we're going to do a little bit more. Now we're going to do a fully integrated Starship, and we're going to test the final descent phase and the flip, which is still a little hairy in my view, but we're going to test that con-ops and see what works, what doesn't work. No matter what happens, we're going to learn something. And it's very obvious as I was saying before, it's very obvious from integrated flight tests 4 to 5 that SpaceX has learned from their previous flights. The booster, we all remember the first flight. They lost a bunch of engines. They basically lost control when they tried to stage at on the very first flight. Next, systems engineer would have come in and said, well, it's very obvious you should have put a sound suppression system on your pad. Like, yes, the acoustics and flinging dirt up into your engines, yeah, that was probably going to knock a bunch of engines out. But they learned. They learned from it. They developed a new system within a few months. They had that ready to go. They tested it, and by next flight, no engine out problems on their booster. Um, and then from 2 to 3, they showed that they could stage, they could hot stage, they could do the flip, they could maybe didn't recover their booster, but they learned something. And you can see that iterative approach of we have a design based on past assumptions, based on past data. We've made some design changes. We've learned from it, and now we're going to fly it with those new changes. And that's a very, very much a systems engineering approach. It's very interdisciplinary. It's very cross-functional. It's looking at the whole system, not just from a booster. It's looking at I have to integrate all these Raptor engines on my booster. I have to integrate all of this very complex plumbing. I've got to have these structures. I've got to have a hot stage. I've got to have grid fins to guide myself back. I've got to have strafes. Big change you saw on the booster is they have those grids on the side. Well, those kind of act like little wings, little lifting mechanisms to kind of help with the trajectory back. It shows that they're learning things. And even though, Starship, it did make it through the atmosphere, it still had some burn throughs, still had some issues with the TPS, but smaller burn throughs. So you're seeing that they're learning where the hot spots are. And as we kind of talked about at the very beginning, they're going to figure it out. Eventually, they're going to figure it out with enough time and enough flights. They are going to eventually figure this out. And particularly as an aerospace engineer, it is invaluable being able to get actual aerothermal hypersonic reentry data. Because in order to get that kind of data, you got to go to hypersonic tunnel, and those are expensive. The models you have to build are also very expensive to machine, very expensive to instrument. And then you spend all this money to get 5 seconds of data. They're getting minutes of data for reentry. It really is. Test data is invaluable. No matter what system you're working on. You can get test data earlier. I can take that and go back and refine design. I can refine requirements. I can refine assumptions. It really is invaluable to doing really good space design. It's how you make good spacecraft.
Do you think this is gonna get like NASA or ESA or JAXA reflect back on how they're doing things, or
I think that for governments, that the way that they operate isn't, I think, going to fundamentally change. Governments, as we all know, they operate the way they operate, and procurements and budget authorizations. Those are not going to change. NASA, unfortunately, I think is going to become a victim of this, and we can see it now. The Starship flight was all over the space world yesterday. Everybody was talking about it. It's the only thing everyone was talking about. Europa Clipper today kind of got some hits, but not the same. The excitement was more is that a Falcon Heavy was flying, not that Europa Clipper was flying. NASA is kind of unfortunately falling behind a little bit in SpaceX and Blue Origin and Vast Aerospace and all these other startups. They're doing the really cool stuff. They're doing the cutting edge science fiction turned into science reality kind of projects. Stuff that as kids we read about. It's like, oh, that'd be so cool if that ever came into being. I can't wait till NASA does that. But it's not NASA doing it anymore. It's these space startups, and that's where the excitement is. I don't think NASA as an organization is ever going to go away. It may just become a scenario down the road where NASA's role, like it is today, just fundamentally doesn't exist. NASA is kind of like the FAA. They're more of an oversight sort of committee. They give launch authorizations to companies, and they monitor space activities. Provide that governmental oversight that is needed. in order for us to be compliant with the Outer Space Treaty of 1957 and all the other subsequent treaties about how governments are supposed to operate in space. But that is probably where NASA is going to go. Is we're even saying with Artemis, SLS is a from all intents and purposes, SLS is one of NASA's greatest failures as an organization. It really is. Um, Starship, in less time, is doing more than SLS. It has more capability, and the price alone is is going to make SLS obsolete. SLS costs $1 billion to fly once. You know, Elon's talking about it, and I always have to kind of take Elon Musk quotes about economics with a grain of salt because it's based on assumptions, launch rates, and various other things. But if he's talking $2 to $5 million for a Starship launch compared to $1 billion for SLS, and Starship can do far more capability than what SLS can do. I mean, it's not even a comparison. And NASA, unfortunately, because they are a administration of the executive branch of the U.S. government, they have to enact space policy, and they're being told that Artemis and SLS and Orion, that is the path forward, and that's what they have to do. I think, unfortunately, it's just gonna, like with ESA and others, they're just gonna sort of have to take a step back, and it's going to be the commercial space companies that are the ones that are leading, this charge into creating a lunar economy and going after and mining asteroids and colonizing Mars and all these other things about dealing with energy independence and creating space-based solar power and all these other really cool things that startups are talking about. It's going to be the startups that are doing those. It's going to be the commercial companies. It's not going to be the big governments anymore.
How do you think advances in AI and robotics factor into mission design?
It's hard for me sometimes to think about how AI and machine learning integrates with any system because it's sort of become the buzzword of of the decade. Everyone's doing AI. Everyone's doing machine learning. Um, I always try to take a step back and say, well, what is it used for? Why do we actually need AI machine learning? And it really is to help. It really is to help us become more efficient with the way that we would do design. And it is really dependent on how you feed in data to a model because machine learning, large language models, AI driven prompts are all based on the data that it's trained with, that it's fed with. I think one of the big challenges in spacecraft design is that most of the spacecraft we develop are one-offs. They're 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 designed for one mission, one very specific mission, like Europa Clipper, that it would be hard to take design data from a Cassini and a Mars exploration rover and a Europa Clipper and a Voyager and a New Horizons and sort of try to have a large language model or an AI prompt to be able to help you design what the spacecraft is. There is still a lot of human interaction within that design space just because there are it's like I kind of said earlier, it's based a lot on experience. A lot of people in this industry are very, very experienced. They know their systems, whether it's power or telecom or avionics, propulsion. They know their systems really well, and they know the things that work and don't work. Um, I think we're sort of the where AI kind of helps us um, is in more of like detailed design that I've been seeing. Like I want to make a turbo pump. Elon Musk's his old saying is, first thing you got to do is make something that has the right capability. So the functional design is the most important, then the optimization, and then the automation. So that optimization piece really comes in with helping, figure out how do you make a turbo pump propeller. How do you still have the strength that you need that has the functional performance but takes away, 30 kilograms of mass? That's how you go from a Raptor V1 to Raptor V3. That's where some of those things are coming in. In terms of mission design, I think that one's a little trickier because it really does depend on what is the mission. What's the objective of the mission? Um, I think easily give a prompt to an AI bot and say, design me a mission to Saturn, to Enceladus, that does this, this, and this, and costs under this price. Because at that point, it's extrapolating. It's not interpolating because there is no data. There is no Enceladus mission that's ever been built. That would be under what this particular cost is. So that's where it gets a little trickier, where because there isn't a lot of data to go off of from a mission design perspective, it's really challenging to, I think, to have an AI prompt help you design a mission when you're basically asking it to extrapolate. At that point, mission designers, we might as well just come in and just do the design ourselves in STK, because we can play around with the parameters and turn the knobs and know what we need to do to get the solutions that make sense to us.
Cool. So, and now with your work at Icon and the Phoenix project, you're helping develop a system that can potentially build structures on the moon. Can you tell us more about what that work, how that works, and what excites you about this project?
So I took a little pivot out of the space program. Not that I think I'm done with the space program, because it's intoxicating. It's hard to leave the space program and not want to come back. Um, but Icon is a really interesting company. It's a startup. Just like there's a lot of those really interesting startups out there that is trying to solve the global housing shortage. That's their primary mission, is to figure out how to 3D print homes at scale to try and answer the housing shortage in the world. I think something I read is there's like a 2 billion shortage on houses needed to house everyone in the world. And they talk a lot about dignified housing for folks who are low income or homeless. It really is a very honorable mission with what they're doing. But the system perspective, we are with Phoenix. We're building a next generation 3D printing system that can do much better than what we currently have with Vulcan, and you can look this up on Icon's website. Vulcan is a truss. So it's basically two pylons with a truss in the middle and a print head, and it follows a print path and does its design. Those are unfortunately greatly limited by the size of the home you can build and the footprint, because the truss can only go so far. So you're limited by the types of structures you can do. Phoenix is a kind of like a Mars rover arm. I always like to use that analogy. It's an articulated arm, so it has 5 or 6 degrees of freedom, and we can essentially this new version, we can print much more complicated print paths, so much more exotic structures. We can print multiple stories with it. We can print underground. The idea is to basically be able to print homes at scale for very, very, very cheap. We're talking being able to print homes for a fraction of what they can be made for today, and much faster. Rather than a home today in the United States can take 6 to 8 months, depending on when the home starts, especially where you live. If you live in Colorado, could be longer, because if you're breaking ground in October, November, we could have our first snowstorm here in the next week or so. So it depends on when you decide to break ground. But with Phoenix, we're talking about building systems, building homes within the span of a week. So at least printing the wall systems, the primary structures. So that's you go from, it takes 8 months to get a home to you sign a contract, you can have a home within 8 weeks. That's paradigm shifting for folks that want to get into the home, but also want to have a home that is affordable for them. Like anywhere else, interest rates everywhere are very high. We're all still recovering from, even 4 years later, we're all still recovering from the COVID pandemic. But a lot of the work that we're learning with Phoenix is going to feed into, as you said, building structures on the moon. If we learn how to do it efficiently at scale here on Earth, now we can talk about, well, how do we do it on the moon? because eventually, if we want to have a permanent, sustaining lunar economy, we got to put people somewhere. And just like on Mars, it costs a lot of money to take something from Earth and put it on the moon, especially if you want to land it. It costs a lot of propellant to put it on the surface. It costs a lot of propellant to get it up into orbit and get it out to the moon. So the idea is, if we can build the system there, the old saying of space logistics, if we can learn to live off of the environment that we're in, it's going to be a game changer. It's going to really is paradigm shifting, where you don't have to take your stuff with you; you can make it there. Um, so a lot of the stuff that we're learning on Phoenix is going to feed into the Olympus program, which is our off-world construction program, and that's really figuring out how do we print structures on the moon, and eventually we'll sort of feed into, well, how do we print structures on Mars? How do we then live off of Mars? Lunar regolith is a little different than Mars regolith, but if you can learn how to build structures with what you've got on the moon, we say the same thing of, we can just extend that to, the only difference is the material is different, but the operations, the con ops, the 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 components and the technologies needed to print are the same. So kind of like with SpaceX, we start with function, something that works. We then optimize it, and then we'll learn how to automate it. And the automation part's the important key, because you're not going to have a astronaut sitting here with an iPad telling this Olympus machine how to build the structure on the moon. We're going to send it instructions, and we're going to say, go do that. So that's really figuring out how to do the automated piece.
Okay, we're as we wrap up, I'd love to hear any final thoughts or advice or announcements you might have for our listeners.
As we've seen over the last couple of days, the space industry is a very exciting place right now. There's a lot going on. Just within the last 2 days, we had Crew 8 undock from the space station. We had a Block 3, a brand new Shepard vehicle that did a test flight. We had a integrated flight test 5 for Starship. We had Europa Clipper. That's all in 48 hours. It's a very, very exciting time to be alive. It's a very exciting time in the space industry. There's lots of stuff going on. And those are just the things that are making the news. That's not all the other stuff that's going on in the startup world and these really interesting concepts that folks are working on. I mean, we've got startups working on asteroid mining, lunar construction, 3D printing lunar structures on the moon, wireless power transfers, figuring out how to make nuclear-based propulsion systems to reduce the transit time from the Earth to the moon, or from the Earth to Mars. There's no shortage of really interesting projects and really interesting. I look at it as really interesting challenges, and that's what draws a lot of people to the space industry. The challenges of trying to operate in that environment are really the hardest you're ever going to find. The space environment, as I've told students before, it's the worst environment to work in because everything about it wants to kill you. You're in vacuum, you have large temperature swings, you've got radiation to deal with, you've got surface charging to deal with. If you want to work on the moon, lunar regolith's like glass. It wants to cut all your harnesses, wants to destroy your mechanisms. If you want to go to Mars, you got to deal with dust storms. There's no electromagnetic field. At least there's a little bit of an atmosphere, but you still have the big temperature swings. Still can't go outside without a spacesuit. So everything about space flight is hard, and that's kind of what draws us to want to work in the space industry. Is we want to solve the hardest problems, and space industry offers the hardest problems, like figuring out how to catch a 27-story tall rocket booster with a pair of chopsticks.
Okay, so where people are interested to follow you and learn more about the news or what's happening, where can they find you or follow you?
I'm on LinkedIn. I try to keep the pulse of the space industry, see what's going on. It's kind of where I pick up all my stories about all these new startups and stuff that's going on. Is there's no shortage of the Space Twitter, Space LinkedIn. It's everywhere. If you want to learn something about what's going on in the space world, you can find it online.
Perfect. Well, Michael, thank you so much for joining us today. It's been a pleasure, and I'm sure our listeners have learned a lot. Until next time, this is Omar Alayli, and you've been listening to the Omar Alayli podcast. Keep exploring.